In this video, we're going to talk about extreme values, or critical points as they're sometimes called, and how to tell if critical points are local maxima, local minima, or neither. So first of all, increasing and decreasing. When is the function increasing and when is it decreasing? What that means is, as we're moving along from left to right, what is the function doing? Is it going up or is it going down? Increasing means it's going up. So I'll highlight that in red. Here we're going up, 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 up. And then here we continue going up, 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 up. For the next segment, we seem to be going downwards, right? So we're going down here, down here, down here, down here, down here, all the way to the bottom. And then we go from there, we go back up. So one way to think about it is, if you're walking along this function from left to right, would you be walking uphill or downhill? So the red regions here represent what are called our intervals of increase, and the blue region is our interval of decrease. So let's write out in set notation what the interval of increase and interval of decrease is. So looking at the interval of increase, we are basically going everything less than, let me do it here, everything less than this point right here at 0. So our interval of increase, we can say, I'll do it in red just to keep it consistent here, x has to be less than 0. And I didn't put less than or equal to because at this point at the top, we're not really increasing or decreasing. We also have another one, interval of increase here, where x is greater than 1. So those are our intervals of increase. Our intervals of decrease, well, we only have one, and it's between 0 and 1. So we can say x is between 0 and 1. Okay? So that's when the graph is decreasing. Again, I didn't put less than or equal to because at those points, it's not actually increasing or decreasing. It's flat, essentially. So we've done this before. How does it tie into calculus? Well, that's the next question here. What can we infer about the derivative of increasing and decreasing intervals? Well, what do you notice about the derivative of the increasing intervals? So for example, let's take the derivative here. Remember, the derivative is just the slope of the line. What do you notice about the slope of that line? Or the slope of that line compared to the slope of this line, or the slope of this line compared to the slope of this line, or this line? Well, you should notice all the ones I did in red have a positive slope, and all the ones in blue have a negative slope. So another way to define the intervals of increase and intervals of decrease are where the derivative is positive, or where the derivative is negative. So our intervals of increase, that's what we're at. Our intervals of increase take place where the derivative, f prime of x, is greater than 0. And our intervals of decrease happen where f prime of x is less than 0, or negative, right? So that's another way to define our intervals of increase or decrease. Now, I actually have another question here, something we missed, something I purposefully left out. What happens at this point of -1? What is the slope of the tangent at that point? If you look carefully, you might sort of see that it's sort of horizontal at that point. Similar to how it's horizontal here and it's horizontal here, the tangent at least. So this point actually has a horizontal slope as well. And we actually made a little bit of a mistake when we included that in our interval of increase, because the function actually is not increasing at that one little point. So we can actually further modify that, our interval of increase, to say x cannot equal -1, right? That should be part of our set right here, right? Because at that point, the function is not increasing or decreasing. It's 0. The slope is 0, essentially. Now, we've already talked about local maxima and local minima, so we can see clearly that this point right here is a max, and this point here is a min. What do we call this point here, though? It has a slope of 0, similar to these two, but unlike the other two, it's not a maximum or a minimum. It just has a small horizontal slope. Well, we actually have a special name for these. These are called points of inflection. Point of inflection. So it's essentially a point that has a slope of 0, or a slope of the tangent of 0, or the derivative equals 0, yet it's not a maximum or a minimum. So these things can happen as well. So let's say we're given an equation, this complicated equation right here, and we're asked to find, are the critical points maxima, minima, or neither? The critical points being the locations where the slope is 0. So it actually is telling us that the slope is 0 at x equals -1, at 0, and at 1. So we have 3 values. Are those values maxima, minima, or neither? How can we find it? Well, one way to do it is to sketch the graph of it, right? If we can sketch the graph of it, we can determine whether those are maximum, minima, or neither, right? But if we didn't want to sketch a graph of it, or we weren't able to sketch a graph of it, like in order to sketch the graph of this, we might need to factor it and do all sorts of fancy stuff, which might be more complicated because it's a 5th degree polynomial. Instead, why don't we check out some values? So we can actually find the value of the function at these 3 points. So let's start off with x at -1. So let's look at f at -1 first of all. If we plug -1 into this equation, we would get 0. So we know the y-coordinate of this point is 0. How can we tell if it's a maxima or minima? Well, one way to do it is if we think about our function, right? If the function was a maximum, we could plug in a point on either side of that. What should we see if it was a maximum? Well, we should see that those 2 points are lower down than that other point. So why don't we try that? We're going to try to plug in f at -1.5. And on the other side, let's do f at -0.5. So we can plug those in. It's not too difficult to plug it in. It's just a little bit of calculator work. If we do it, we get that f at -1.5 is about -1.6. And f at -0.5 is about 0.5. So what does that tell us about this point? Is it the highest point in a maxima, or is it the lowest point in a minima? Well, it actually, if you notice, on one side of it, it's negative, and one side of it, it's positive. So it's actually probably, over here it's negative, and over here it's positive, which means it's actually neither, right? Because this point over here is lower, and this point over here is higher than this value. So we could graph it, but just by this, we can tell that, therefore, x equals -1 is not a maximum or a minimum, it's our point of inflection. Right? Now, if you're really paying attention, you might realize that the function that I actually gave you here is actually the exact same function as this one that's over here. I just gave you the equation for it. So you'll notice that this makes sense. We plugged in a point to the left and to the right, and we got that the one on the left was lower, the one on the right was higher, so it must be a point of inflection, because on either side of it, it's, higher and lower, so it must be in between, must be that. So we can also do the same thing for f at 0. Right? We know f at 0, if we plug in 0 into that equation there, we'll get that f at 0 equals 1.4. That's what it'll come out to. So if we wanted to check a point on either side of that to see if it's lower or higher, we can check something like -0.5, which we already checked over here. And why don't we also check f at 0.5, right? And if we do that, we actually get a value of -0.3. -0.3. Now, what this tells us, if we look at either side of this, so we know the point that we're considering at f at 0 is 1.4. On either side of it, you'll notice that the value, the y value, is lower down. So if we have a point and on either side of it's lower down, we know it has to be a maximum value. So therefore, x equals 0 is a local max. So that makes sense. And you could also do the same thing for f at 1. If you do f at 1, you should see that it's a local minimum. So you can plug in a point, say 0.5, which we already have, and maybe 1.5. And you can see that it actually ends up being a minimum, which agrees with our graph over here. We had a local maximum at 0 and a local minimum at 1. Now, this process is a little bit tedious to keep on plugging in points to our function. It's a little bit annoying to do that, but it is a way, this is sort of like the brute force way to tell if something is a maximum or a minimum, to plug in a point on either side. And in fact, you can go even closer than being off by 0.5. If you want to make sure that you got it right, you could go off by 0.1 less and more to see. This, again, is sort of the brute force way. We have a little bit more of an elegant way to do that. And the way to do it is called the first derivative test. This is a very useful test which allows us basically to check to see if a point that has a slope of 0 or tangent to slope of 0 is a maximum or a minimum. So what we need to do to understand this is to go back to our drawing here. We saw for something to be a local maximum, it had to be increasing on one side and decreasing on the other side. For something to be a minimum, it had to be decreasing on one side and increasing on the other side. And then there was a point of inflection, which was increasing on one side and increasing on the other side. So what you see is that you see at each of these points, the slope is 0, first of all. And second of all, whether it's increasing or decreasing on either side tells us also if it's a local maximum or a local minimum. So, for example, let's look at that same function. We know the slope of the tangent at that is 0 at blah, 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 blah. So the question is, first of all, let's find the derivative of this function. Because in order to check if the derivative is the function is increasing or decreasing, we can use the derivative. So the derivative of this function is just 0.2 times 12 times 5 is 60x to the 4 plus 60x cubed minus 60x squared minus 60x. So there is our derivative. That's a lot of 60s. So we can actually factor out a 60 here to make it a little bit easier to work with. If we factor out a 60, 60 times point is just going to end up being a 12, x to the 4 plus x cubed minus x squared minus x. And we actually factor out an x as well, just to make it even easier. 12x x cubed plus x squared minus x minus 1. So this is a little bit easier to deal with, obviously. It's a little bit of a simpler function than this original function was. And that's the point. A lot of times, especially when you're working with polynomials and some other functions, it's a lot easier to work with the derivative of the function than the function itself. So basically, in order to check if a point is a maximum or a minimum, for example, the point x equals -1, we want to know if the function is increasing or decreasing on the left and the right. So the way we usually show the first derivative test is as a table. So this might bring back some memories of tables in other courses. We want to set up a table with all those critical values. So f prime of x is the thing we're concerned with, and we want to set it up with our critical points. So our critical points are -1, 0, and 1, right? Those are the places, I'll label those critical points. Those are the places where f prime of x is equal to 0, our derivative equals 0, right? And in a lot of questions, you'll have to solve for those. I'm giving you them here just to make our question a little bit easier, right? I gave it to you right up at the top. So our point is, if we can check if the derivative is positive or negative in each of these ranges, we can tell if the function is at a maximum or a minimum. So all we got to do is we got to plug in a test value in each of these cases. So here we can plug in, for example, -1.5. Here we can plug in -0.5. Here we can plug in 0.5. Here we can plug in 1.5. So if we plug in those values, right? For example, if we plug in -1.5 and you do that, you plug it into here, you should see that the value comes out to be a positive value. Let's do it in blue. A positive value. If you plug in -0.5 into that equation, you'll also see that it comes out to a positive value. If you plug in 0.5, you notice that comes out to a negative value. And if you plug in if you plug in positive 1.5 into the derivative right here, you will get a negative value. Oh, sorry, that's wrong. You'll get a positive value. That makes more sense. So once we have this table, we actually have a pretty good understanding of the function, because what this tells us is when x is less than -1, the function is increasing. When it's between -1 and 0, the function is still increasing. When the function is between 0 and 1, the function is decreasing. And when the function is greater than 1, the function is increasing. So essentially what we can say is here the function is increasing, here the function is increasing, here the function is decreasing, and here the function is increasing. So from this little sketch that I drew just with those lines, you can sort of see this point here at 0 must be a maximum, because we're going from an increasing slope or a positive slope to a negative slope. So in between, this has to be a local max. This point right here goes from, at x equals 1, goes from a negative slope to a positive slope. So if you sort of were to connect those, you'd see that this occurs at a local min. And over here, if you plugged in -1, you see it goes from a positive slope to a positive slope. The only way it can go from a positive slope to a positive slope with a 0 in between, a slope of 0 in between, is if it's a point of inflection. I'm actually going to call that POI to shorten. So that must be a point of inflection. So looking back at our original graph, remember this is the same graph. You can see here, we go from a positive slope to a positive slope, point of inflection. We go from a positive slope to a negative slope. That means local maximum. We go from a negative slope to a positive slope, point of inflection. Local minimum. So there you see, that's called the first derivative test. And again, usually the way we express it is in a table. And the table has the derivative, and we just check to see whether each range between those critical points is positive or negative, increasing or decreasing, and we use that to determine whether something is a local max or a local min. So I'll let you summarize the first derivative test in your own words, but basically those are the three cases that it can come out with. We can learn that something is a point of inflection, a local max, or a local min. This will actually help us a lot when we're sketching functions, and you'll see that in the future.